bond polarities and dipole moments of molecules turn out to be really important in the functioning, and we'll see this in later coursework and in higher level courses in organic and in biochemistry. An awful lot of the functioning of actual molecules really determines on polarity, so it's a very important topic. It's a little bit tricky too because it involves 3 dimensions and thinking in geometrical terms. So remember, we talked about our covalent bonds and we're sharing of electrons, but we said that you can have cases where they're not shared equally. If you have atoms of different electronegativities, then there's a dipole moment because there's an unequal sharing of those electrons. Again, we're talking about things that have a dipole moment or a difference in electronegativity bigger than 0.4 and less than 1.7. At 1.7, we're going to kind of sort of declare it enough of a difference that there's probably been a transfer of electron and it's an ionic bond. So we're talking about polar covalent bonds. And it ends up resulting in a charge separation. So I end up having, because the electrons are closer to the more electronegative atom in these cases, I end up seeing a partial negative charge on the more electronegative atom and a partial positive charge on the less electronegative atom. Again, I don't really want to put plus and minus like we've done with formal charges because it's not a full charge. I haven't seen a transfer of electron, but there's just a general pull of them towards one. So to indicate that it's just a partial charge and not a complete formal charge, we use this small delta this is a small Greek letter delta, so this is what we use to indicate that there's a partial positive charge on hydrogen. And again, I chose hydrogen to be the positive one because it's less electronegative than X. In this case, X would be partially negative because it has a higher electronegativity. And I'd have to have a difference of at least 0.4 to be able to kind of show this and talk about having a significant dipole moment. Drawing it can really help. So when I draw it, first I have to determine the dipole. So I'm going to have to get the electronegativities of both atoms that are in the bond, subtract them from the higher one minus the lower one. And then I'm going to draw an arrow from the lower one to the higher one, or put a sigma plus on the lower one and a sigma minus on the higher electronegativity atom. And I can actually put the difference on top of the arrow if I'm using an arrow to kind of indicate the size of the dipole moment. And that can be pretty helpful. We'll see that that's going to be important when I start talking about molecular dipoles. So we could do this one. How do you want to order these bonds in increasing polarity? I'm giving you 5 different bonds. So think about how you would need to, what you need to do that. So up till now we were talking about a bond dipole, just talking about a single bond between 2 atoms. But what happens when I have a molecule with multiple bonds and I have a center atom and more than one bond? What happens to the molecular? Can I have a molecular dipole moment? And the answer is yes. The molecular dipole moment is the sum of all the individual bond dipoles. But it has to be a geometric or a vector sum. It can't just be adding up numbers. The direction matters. If you have 2 poles both pointing to the left, they sort of add to each other. But if they're pointing in opposite directions, they kind of cancel each other out. So the direction is important. So I can add them vector-wise. If you haven't had a lot of practice with vectors, one of the things we can do is, especially if it's in a planar, is I can slide the arrows that are in the direction of the bond. I would have to draw the molecule according to determine its Vesper shape, and then I need to draw it in the representation of the shape as the bond with the right bond angles, and then I can draw the dipoles in the correct orientation, and then I can slide them end to end. So I'm going to take one and leave it alone and take another one and slide it so that the point of the first one is right up next to the tip of the end of the other one. So I'm going head to tip, and I see both of these, and then I can complete from the original start to the original arrow ending. The final arrow ending will be my overall dipole moment. So I can see for oxygen in this water, I have two competing dipoles going in not quite opposite directions, but in 120 degrees opposite directions. And when I add them together, I do get a net dipole in the direction towards on the oxygen away from the other hydrogens. So this would be what the dipole moment of a water molecule looks like. Again, just kind of working in more detail with water. I would first draw my Lewis structure of water. I can have my lone pairs on the oxygen or not show them. It turns out it's not going to change. Having the lone pairs there would help me determine that the electron geometry and the molecular geometry is a bent molecular geometry with an angle of about 109.4, a little less because I have two lone pairs there. And then I'm going to need to determine the bond polarity. So I would look up the electronegativity of hydrogen is 2.1 and of oxygen is 3.5. And when I subtract them, I get 1.4. Oxygen is the higher electronegativity, so I point the arrow along the bond, direction of the bond, towards the oxygen, since oxygen is the more electronegative. I could put a 1.4 on top if I wanted to. I do the same thing with the other bond, except it's pointing in a different direction. And while these are pulling apart, it's the general idea of whether they're pulling apart or pulling together. In these cases, they're pulling together, and I see that the overall bond dipole is going to be kind of towards the open side of the oxygen atom on the water molecule. I can also get no net dipole moment molecules. One way I can get a nonpolar molecule, this is not a nonpolar bond, but a nonpolar overall molecule, is if the molecule has no polar bonds. If there are no individual dipole moments in the bonds, then there's nothing to add, and then I end up with a nonpolar molecule. But the far more trickier one is I could have a molecule with symmetrical equal length dipoles. So they all have the same number difference and they're all in geometrically symmetrical orientations, and they cancel each other out. You know, this is a little bit like a tug of war. If I just had two and they were pointing in exactly 180 degrees opposite to each other and they were pulling with the exactly same strength, so they had the same difference in electronegativity, the same dipole moment, they would cancel each other out, kind of like if you have equally matched teams in tug of war. And in those cases, we end up with a nonpolar molecule. It has polar bonds, but a nonpolar molecule due to symmetry because of this canceling out effect. And this is really challenging to recognize. So we want to be practicing looking for those geometrically similar molecules, symmetrical molecules where this can happen. So again, let's sort of show a couple of these canceling geometries because that's the part that students tend to be confused about. So if I have two equal magnitude dipoles pointing in opposite directions, 180 degrees apart, that will cancel. If I have three equal magnitude dipoles and they're in a trigonal planar formation or 120 degrees apart, that will cancel. And if I have four equal magnitude dipoles in a tetrahedral orientation or 109.5 degrees apart, they will cancel out. So I'm looking for these. I can also have canceling effects with the larger than 4 with the trigonal bipyramidal and the octahedral geometries, but we're just kind of seeing the general idea of it. One trick that can help identify symmetrical cases is looking for geometries where there are 0 lone pairs on the center atom. So the molecular geometry is the same as the electron geometry. In those cases, if you also have all equal dipole moment magnitudes, which is generally having all the same outer atoms. So I have a center atom bound to identical outer atoms like CH4 or CCl4. And could also be atoms with the same electronegativity, then those dipoles are going to cancel. So I need the proper geometry, and the geometries that can cancel are going to be ones with 0 lone pairs. And I also need to have identically polar bonds. And just to reiterate, there's 3 different kinds of polar cases. So I have 3 different kinds of molecular dipoles. I can have nonpolar or no dipoles, and there's 2 types of them. There's ones that they're a nonpolar because there is no polar bonds. There are no dipoles. All bonds are nonpolar. And then I can have nonpolar that's canceling due to symmetry. So I need to have at least 2 polar bonds for that and a center atom with no lone pairs. And all of the bonds have to be equally polar, so equal magnitude dipoles. And then I can have polar molecules, which are ones that have to have at least 1 polar bond, and they have to be either not identically polar or not the proper geometry, and then they won't cancel out. So I have kind of 3 different conditions, and I'm going to first begin by looking at the polarity of the bonds and assessing. If I don't have any polar bonds, it's nonpolar and I'm done. If it's polar, if I have some polar bonds, then I'm looking for symmetry cases to decide, is it polar or is it nonpolar by symmetry. Here's a couple of examples we'll keep looking through. If I have 2 identical polar bonds pointing in opposite directions in a linear case, that's going to be nonpolar. If I have 3 identical bonds in a trigonal planar case, that's going to be nonpolar by symmetry. Those are canceling cases. And then I have lots of polar cases. So if I have a trigonal pyramidal that has lone pairs on that center atom, then I have a polar molecule if I have at least 1 polar bond. If I have 2 polar bonds that are in a bent geometry, even if they're identical, they won't be able to cancel out. And then I have this case of 4 identical polar bonds in a tetrahedral arrangement that would be nonpolar. So those are some pretty common cases that we tend to see quickly and often. And again, trying to recognize that and practice with this. This is a challenging topic. Here's a few more examples. We see that these, here I have iodine chloride, and it does have a net dipole moment. Again, there's only 1 polar bond, so there's nothing that could cancel it out. Here I have CO2, and in CO2, if I tried to add the 2 together, I end up back where I started from. So these are canceling dipoles. I have water. It could have been a canceling dipole, except it's not linear. It's bent, and that bent shape means that they can't quite cancel each other out. And then I have carbon tetrachloride. That is a nonpolar by symmetry. So I have 2 nonpolar by symmetry, 1 nonpolar by, 1 polar because there's nothing to cancel out, and another polar. So the 2 on the left are polar, and the 2 on the right are nonpolar, even though they have polar bonds. Practice by taking these 4 molecules and determining if there's what the net dipole moment is, or if his net dipole moment of 0 would mean it's nonpolar. You'll need to start with a Lewis structure. So again, get really good at these Lewis structures and then go from there.